For today, we were going to start on chapter 12, which covers eligibility traces and the TD lambda algorithm, which we're going to spend most of the time working up to this. This is sort of connected to the TD0 algorithm we had from part one of the book, which was the original temporal difference algorithm we had. And that was, back in these, I guess it was chapter 6, we had introduced temporal difference learning with this update target that uses bootstrapping. This is in contrast to Monte Carlo learning, where you take all these rewards and sum them all the way to the end. But then in chapter 7, we had introduced this n-step learning method, where if you just look one step ahead and then use some value estimate, this is like the TD0 algorithm. And that is like, this name is sort of specially connected to this. These other things we had called like two-step TD, three-step, up to n-step, and then infinite step was just Monte Carlo learning if in fact there is this terminal state at the end of the episode. So these were all just different ways through sampling, sampling a trajectory through the environment where these open white circles are states and these black circles are actions. And depending on how far you look ahead in the future before you stop sampling and use this bootstrap target, you have this different value of n. And back in chapter 7, we could sort of use a method that was a specific value of n. And the idea in this chapter is to replace that with a more general method, which will combine a lot of different values of n, and at the extreme ends can either, where lambda is 1, it will be equivalent to Monte Carlo methods, and if lambda is 0, it will be the TD0 method I had just shown, where you just look one step into the future. So there is going to be a way to compute all this, which occurs in an online fashion. So you can do it step by step. But to define everything, and initially, we're going to look at, at a definition that would require us to look forward in time. Some, really theoretically, until the end of an episode, if it exists, to compute any of this. But some of the exercises in this chapter show how if you do this in real time, you can end up computing incrementally what ends up being the same as if you had waited until the end of the episode. So that's what this eligibility trace vector, which is going to be defined later, is going to be used to keep track of that. So the first thing we have to do is introduce this new target. Now, we had already looked at that was this diagram I showed here, the n-step return. And the n-step return, which is indicated in this fashion where t is some time step we're on, and n is some number of steps into the future. And depending on the value of n, that is how many reward values that you sample. So these are like, if you're at step t, on that transition, you get this reward t plus 1. On the next step, you get this. And this is just the discounted sum of rewards, which normally, if this was just g sub t without the colon here, this sum would just go on forever and continue to be discounted until you reach a terminal state, or if there's no terminal state, it would just be an infinite sum. But the n-step return, we cut off the return here. There is this caveat that if the episode ends before this, the return will just be shorter. The number of rewards will be shorter, and it will be like the full return in that case. But otherwise, this is like, if the end of the episode is farther out than n, then we truncate this sum and use this value v hat to finish off the sum. And this value is the bootstrap target, which is whatever current estimate we have of the value at this state, discounted the appropriate amount into the future. So we had looked at different n-step returns, like depending on the value of n, you have these different returns, and that's all of these listed here. And as an example in the chapter, there's this idea that, okay, well, instead of just restricting ourselves to like a two-step return and a four-step return, as we have here, if we have a full episode of data to look at, then we could combine these two targets. And the way these diagrams indicate what's being calculated is this is like the coefficient of how much we're averaging this, whatever the n-step return is. So this is just saying that these are going to be just averaged together with 1/2 weight on each. In the, writing it out like algebraically, you have this 1/2 of the two-step return and the four-step return. But this is sort of just the visual diagram indication of that. So does this make sense to everyone, what the diagrams indicate and what each n-step return is? Because like so far this is all stuff we had previously defined.
Well,
Yes.
it seems to make sense, given the goal state and then the decaying rewards, and then having basically a two-step and a four-step combination, essentially. I think that makes sense.
Mm-hmm. Okay, so yeah. Hey, Kevin, do you have a question, or I'm just going to mute you if you don't have a question? There's some background noise. Okay, so the lambda return, now this is like a new definition. So the lambda return, we're going to define it like this. Now, it's a little weird because remember, like this G is already like a discounted sum here where the discount rate is gamma. Now, the lambda return is something where we're going to take all of the different n-step returns that we could have and average them together with a new parameter, which this lambda parameter, which later on we're going to call it the, I believe, trace decay parameter or something like that. But it's another decay parameter. And given like whatever time step t we're at, we have access to all of these, n-step returns into the future. And in theory, if there's no, if there's some terminal state, there is a finite number of these practically, because, once your n goes up to the terminal state, you can't go beyond that. But if there is no terminal state, then this will just extend forever. And again, because we're taking a sum which in theory could be infinite, we do have to make the sum finite. And that's what this lambda is doing. So the further out we look, like in the extreme case where, when n reaches infinity, this is just the Monte Carlo target. And that return is going to contribute less, or it's going to contribute less by this power of lambda than the earlier returns. But and this is intentionally constructed so that, like, if you look at this sum, if you just take the lambda here, like let's say all the g's were 1, this infinite sum is just 1 minus lambda, right? So this ensures that for whatever finite values of g, that all of the coefficients end up summing to 1. So this is a way of sort of constructing an infinite, an average of potentially infinite terms, where they're not all a constant weight, right? Like we couldn't actually take this average if we just said we want to count all of these equally, because in the case where there's an infinite number, as we're computing it incrementally, each term would contribute, 0, because if you take an average of infinitely many things, the limit of the coefficient goes to 0. So this is a way where, depending on the value of lambda, you actually have finite contributions along the way. Unless, of course, in the extreme case, like notice, like you can take the limit here as lambda goes to 1, but right, like this formula doesn't, like this formula like written here will stop functioning when lambda is 1, right? Because it's going to set all the weights to 0. But in the limit as lambda goes to 1, and that corresponds to the Monte Carlo return, and it's sort of a pathological case of this, because practically you end up just weighting this single one fully, and these stop mattering. But to see what these weights look like, there's this graph here, and I have a version of the graph which might make things a little easier to see. So this definition here considers that, n out to infinity. So this curve here is what the weights would be if you could access the n-step return all the way out to infinity. Now, if there's a terminal state at this time step t, then all of the return values that would be out here just remain the same value, right? Because like whatever the g was up to this time horizon, there are no future returns after you reach the terminal state. So you have to take this final return, whatever it is, whatever the value of t is, and you have to assign it the weight of all of the other terms that would be included if you actually did the infinite sum. So this is like the area, under the curve, or like the sum of all these terms going out. This is like this tail term, and it happens to equal lambda to the big T minus T minus 1. So here, if this is showing the same curve, but just what the coefficients are, the starting coefficient of the first term is just 1 minus lambda. And this chart is just normalized. So like this would be a weight of 1 here. This is 1 minus lambda. And then the coefficients decay into the future. This is going out. This is if lambda is 0.5 and there were 25 steps until termination. Now, if I make this shorter, what will start happening, like right now, it looks like the weight contribution of the return out to the terminal state is very low, and that's because with this value of lambda, it's decayed all the way down. But these bars all have to sum up to 1. So as I shorten the number of steps until termination, now these first 3 weights decay, but now in order for this sum to be 1, this is the contribution here from the final term. Here I'm showing what the actual value is. So it's like this area sort of all added up together out to infinity. And it's just equal to this value here. So you can see is this, and then in the extreme case here, I'll put this back out to a higher value. So the lower the value of lambda, then the closer we are to only considering the short term, like low values of n. And you can see that these contribute almost all of the weights, especially if we're at a part of the episode where we're far away from the terminal state. As I increase the value of lambda, what happens is it sort of, in this first part, it evens out the weight contribution because the weights aren't decaying as quickly. And then it also forces more of the weight to be in this this Monte Carlo target where we go all the way to termination. But then, if I send this out farther, then there's going to be more of these individual end step returns to fill in along the way. So less of the weight will be here. But this is just the result of how this formula works. Like as you make big T larger, or the number of steps to termination, then this weight shrinks, and this weight also shrinks if lambda gets smaller. But yeah, if we go to the extreme case, where if we make lambda larger and larger, we are just evening out the weights throughout this. But because if we have a problem where there is a terminal state, what it ends up doing in the limit is just putting almost all of the weight into this final term, which in the extreme case here, all of the weight is on this term. And I guess that's because, I'm sorry, of this formula here. So notice if we make lambda 1, it completely wipes out all of these weights. And then, this lambda return just becomes the Monte Carlo return, G sub t. And that's what happens in this extreme case. And then if you make lambda 0, in this extreme case, right, we have the TD lambda where now the weight on the one-step return is 1, and all the other weights are 0. So those are the two extreme cases. And then everything in between, as I increase lambda, we just place more weight on these further out returns. So I know that it's like what's a little confusing about this is that each of these G's are themselves a discounted sum. But what I'm showing here is not the sum of rewards, but the coefficients on the sum of the individual end step returns, each of which is a sum of returns like indicated here. So now we effectively have two different discount rates. One of them is the gamma, which is part of how the problem is defined. And then this lambda, which is not really part of how the problem is defined, but just a solution parameter, like something we're going to use that may lead to faster convergence, right? Because in theory, like all of these should, in the tabular case, all of these did actually converge to the same values, all of these targets. In the case of function approximation, there actually is a different target that all of these reach, just like we saw with TD0, the TD fixed point, which this estimation method or the semi-gradient method converges to, is not the same as what the Monte Carlo method would converge to. And that's going to be the same situation here, but practically it ends up being quite close to the true target, and that's more of a subtle issue you don't have to worry about right now. But the value of lambda is just like with these n-step methods from before. We chose a different value of n not because it changes the problem, but because an intermediate value of n seemed to converge faster or be more efficient at using samples. And this technique is about, right, all these G's are using data that we're collecting from the environment, like these reward values that we're sampling. So the purpose of this method in choosing a value of lambda is that the value of lambda we pick might make more efficient use of this data. And the claim is that quite often the best value of lambda is some intermediate value, like it's neither this target here, the 0 target, or the Monte Carlo target out here, but some value, in the middle here. And this is able to make more use of all of these different targets, whereas if we go back to the n-step return, each one of these would just be if we had put 100% of the weight on like this one or this one, as opposed to combining them together with this sum. So it seems like this is easier to deal with of just having to deal with one time horizon, but it turns out there's going to be an easier way to compute this thing, which actually looks more complicated, but there's a pretty straightforward way to compute this in an incremental way that looks a lot cleaner than the n-step methods we had in chapter 7. So any questions about this definition and how the weights work as we vary lambda from 0 to 1?
Well, it looks like it makes sense, given how the goal state of the lambda exponentially decays, and how it's basically the summation of different amount of steps, and then depending on if there is an end state, then the t parameter can be larger or smaller, where if you have lambda equals 1, everything will be at the end, which is similar to Monte Carlo methods.
Yeah, I mean, to be clear, like lambda equals 1 is identical to Monte Carlo methods. So this algorithm will end up subsuming all the previous, I mean, this covers TD0 and Monte Carlo. What this algorithm does not cover is like a specific n-step method, like n equals 3, but it's unclear if this is, useful. I mean, this ends up including the 3-step target along with many others. So
basically, compared to just having an n-step method, this is basically having a range of how much importance to give to the look back on a scale of 0 to 1, where 1 you don't look back at anything, which because it is Monte Carlo, and then 0 you look back at everything.
Well, I mean, here we're really looking forward. I mean, like the way this is written out, we're at a certain state here, and we're looking forward either one step or out to termination. And these are the sort of forward-looking, discounted return n-step returns.
Yeah, look forward. That was a correction that was needed. All right.
Yeah. So it seems good, everyone.
Yes.
All right. Okay. So it might be there are a couple of these early exercises in the chapter that they're kind of algebraic. So I don't know how easy it is going to be to follow what like I've already written down here, but I think it is helpful to get a better sense of how these targets work and how the math works. So I'm going to go through at least the first few exercises, even though it's kind of math algebra heavy. So for the first exercise, it says just as the return can be written recursively in terms of the first reward and itself one step later, this is from a much earlier chapter, chapter 3, so can the lambda return derive the analogous recursive relationship from 12.2 and 12.1. So actually, let me see, I'll go back. So here's 12.1. This is what, this n-step return is, and 12.2, this is the lambda return. So the sort of like, here, I'm just going to write this down. The general idea they're asking for is like, we had already seen much earlier in the book where when we had this return, like G sub t, like this is just RT plus 1 plus gamma RT plus 2, and we go out, either to a terminal state, but let's just say this, extends indefinitely. We keep raising to higher powers of this. And then, the idea was if you write down this G sub t plus 1, if we just replace all the t's with t plus 1s, then we get RT plus 2 plus gamma RT plus 3 plus, gamma squared RT plus 4 plus da da da. And the idea was to observe here that, we can actually express G sub t is equal to R t plus 1 plus, and then if you look at this whole expression here, this is just gamma times, G of t plus 1. So, we had this simple sort of relationship for the regular like Monte Carlo return. And then, we have this other expression where we have G, G sub t to t plus n, and it's similar, but we end up, cutting this off where we get gamma to the n, and then, this bootstrap target here. I believe this is, but something like this. And the idea is we want to now like try to see, like, can we write down a similar expression where we like also shift this forward one step in time, right? And you're going to see it ends up looking similar. But if I were to continue with this, you end up just building up another recursive relationship. So that's what I'm showing here. So this is the end step return written out, just, t to t plus n. So this is showing, the first n, there's n of these rewards, and then here's the bootstrap target, and here is whatever this state is at t plus n. And then you can write out, you can shift, actually here, what I've written out is I'm only shifting the first part of it forward, right? So I'm actually keeping, yeah. So I'm taking the return out to the same horizon. So this is effectively one fewer step into the future, right? Because here I'm starting, I'm shifting the starting point forward one time step, right? So then this endpoint, like bootstrap value, is still the same, but all the powers of gamma are one less. So using the same observation we did for the regular Monte Carlo return, you can write this down in a similar fashion, where you have an expression for this n step return in terms of r sub t plus 1 plus gamma times this shifted one in the future. And I think in this exercise, it's of one step later. Yeah, because there is another thing that you could define here, which is you could shift both ends of this forward, so you were shifting the starting point forward and the endpoint. And the difference there would be this would be at a different state. So you'd have like the difference between the bootstrap estimates at a state and then one step in the future. But I don't think that is the intention of this exercise, because it makes, it makes the calculation messier, and it doesn't really give you what you want. So this is just writing the n step return recursively. And then this is equation 12.2. This is the version of it, that goes out to infinity. This is a little easier to deal with than the version where you have this extra term here. So in order to see like how can we express this, because like the goal here is to come up with some expression for the lambda return where we have something plus the lambda return shifted forward some amount, right, to t plus 1. So here I've replaced, this is just replacing this expression for the n-step return with this recursive version here. And then if you group the terms, so now we have this term which is a sum of lambda, and we can pull this r sub t plus 1 out, right? So this is just separating the two terms in the sum. Now this infinite sum, right, this is the sum lambda to the n minus 1, starting at 1, you can shift the n back to 0, but this sum is just 1 minus lambda. So that ends up canceling out and just leaving r sub t plus 1 in here. And then we have left, this n-step return, which is shifted forward one step. But the sum is still over, starting at n equals 1. Now, if you write out, because I've shifted the first step forward, notice that if you go back here, like normally, like n starts at 1, right? So if n is 1, this is the return from t colon t plus 1. Now, this expression, like if you have t to t, so in the colon, like you're saying that we're not even looking one step into the future, we're looking 0 steps into the future. That is just defined to mean that you get rid of all these samples and you just replace it with v hat. So that's what I've written here. Right? This is just the return of t colon t is just defined to be whatever the bootstrap target is of the state at time t. So when you expand this out, right, because I've shifted this starting point forward one step, notice that now the first term here looks like that. It's g t to t plus 1. Now, these terms, you can take the lambda out, and then what you're left with is this sum here, which ends up just looking like this equation for the lambda return, where there's just an extra lambda multiplied by this sum. But that's only after we pull out this first term for g, where we have t colon t, so we just replace it with v hat. Here, and here I've just written down, like, if you just increment this to t plus 1 here, you end up with, you can just write out what all the terms look like, and you get, like the first term is t plus 1 to t plus 2, then t plus 1 to t plus 3 going out. And that's exactly what we have in the brackets in here. So here, there's just 3 terms. We have the reward term where the coefficients canceled out. And then there's this gamma, the 1 minus lambda, we still had multiplied, and the first term in the sum. And then there's the remaining sum, which is just the same as the lambda return shifted forward one time step, but also multiplied by lambda. So, right, this we can replace with v hat. And then this is the final expression we have, the final recursive expression for the lambda return. So we go back, right, like this was the recursive expression we had for the regular return, for the Monte Carlo return. And then we have this expression, it looks pretty much the same, this n-step return shifted forward. And then this looks almost the same, but there's this extra term here, right? In this equation, we don't have to worry about the bootstrap target for this recursive expression. But for the lambda return, we actually we have this extra term here. So there's a lambda and a gamma times the lambda return shifted forward one time step. And then there's this extra term which depends on v hat. And you can see here what this recursive expression is in the extreme cases. So if we set lambda to 1, then this term goes to 0. And then we end up getting r of t plus 1 plus g of this. But right, if you expand out this recursive expression, you just get the discounted sum of rewards, which is the Monte Carlo return. So that checks out, because we said if lambda is 1, we should recover the Monte Carlo return. And then if lambda is 0, then this term goes to 0. This is just a 1. And we just get the recursive expression, which is the reward plus gamma times v hat of the next state. And this is just the one-step TD return that we had used before for the update target. So, it's just a sanity check on this. At least at the two extreme ends, it works. And this should be the correct recursive expression for the lambda return. But, this also means that if we initialize the lambda return, well, what the algorithm's going to do, kind of like what we did before, is if we have an episode, which is going to be like a list of all these rewards going into the future, if we start at the very end, right, where there's only one step into the future, then there's only one return to consider. So here we're like, this subscript part is just big T minus 1. This is just going to be the reward we get right before terminating, because this is going to be 0 at this point, at the end of the episode. So we can initialize our sort of final value of the lambda return, and then we can go backwards to all of these rewards, stepping backwards, and we can use this formula to compute the lambda return at big T and then at big T minus 1 and big T minus 2, where big T is the end of the episode. And if we start at the end and work our way backwards, we can get a value for the lambda return at every step without wasting any computation. Because otherwise, if we're starting at the beginning here, like if we were to compute this without the recursive formula, then for every state we're in, right, we have to compute all of these n-step returns going forward and then average them together and then redo that entire process at the next state, because like all the discount rates are going to be different. And that's very inefficient. But this recursive formula is very useful but I mean, it's only useful if we use it going backwards, right? Because we have to, we can get the answer to this as long as we know g of t plus 1, which is one step in the future, which normally we wouldn't have this. But luckily, because of this formula and the fact that once you reach the terminal state, there's no future reward, we can initialize this at the end with just the final reward value. So that's sort of the trick that lets you compute this efficiently going backwards. But I'll show in one of the algorithms the actual function that does that. So it might be easier to follow if you actually read this or work out the algebra yourself. But hopefully these sort of sanity checks for the extreme cases of lambda prove that this is the right recursive update formula. This is computing the same thing, but for the this more complicated version. It ends up getting the same exact answer if you use this form of the equation. It's just a little more cumbersome. So does that make sense, everyone? Like this formula is very valuable to have because it allows us to compute this in like one sweep through all the rewards instead of having to compute the same sum multiple times. Okay, well, if there's no questions about that exercise, we can exercise 2 is not it doesn't really matter for reinforcement learning. It's more of just a common way to think about weight decay. So it's a pretty simple question. It's just saying what is the half-life? So like depending on the value of lambda, if we consider like the weight on the first return value to be this value of 1 minus lambda, can we express the n for which the weight is 1/2? I'll just sort of spoil a little bit of it, which is that if lambda is 0.5, it should be pretty obvious to everyone that the weight on the second term is 1/2 the weight on the first term, just because it's going to be multiplied by lambda, which is 0.5, or 1/2, which is the value we're looking for. And then as lambda is larger than 0.5, that half-life is just going to be extended out. I mean, typically you wouldn't consider any lambda less. Well, no, that's not true. You could consider lambdas all the way to 0. The more problematic values of lambda are actually further out, closer to 1, precisely because you're including, it becomes more unstable when you're including too many of these weights going far into the future. But the half-life, it's pretty easy. If we consider this is common among all of the coefficients. So we really care about, at n equals 1, this term is 1. So we just want to know the value of n for which this is 1/2. And then you just do some algebra with logarithms, and you get this value for the half-life. So here I already said if lambda is 0.5, then the half-life is 1 step, right? And then as lambda approaches 1, the half-life approaches infinity, as you would expect, because the weights are decaying very slowly in that case. And then as lambda is less than 1, you just get a half-life, which it doesn't really exist anymore because the weight on the second term will have already dropped by more than half of the starting term. But yeah, this is a pretty trivial exercise, but it's just, it gives you some intuition about what the different values of lambda mean for how quickly the weights fall off. Okay, so now we're going to use for this, like the first sort of algorithm, though, we're going to use the lambda return to estimate something. We're going to make use of this recursive formula, definitely. But this algorithm isn't actually like written out in the book. What is written out in the book is the weight update rule. And this weight update rule, it's a semi-gradient rule. It's the same as all the other semi-gradient rules we've seen already, where we have the gradient of the estimation function. And then what's here is the delta that we're using. And here, the delta is just whatever the current estimate is. And then this is the target value. And before, we had this target value was either the TD0 target, which was this, right? This is the like one-step TD target. And then we had the Monte Carlo target where we just have G sub t there where there's no lambda. And now we're going to try to use the lambda return target, right? Where depending on the value of lambda, this could be anything from the one-step return to the Monte Carlo return and everything in between. So it seems, simple enough. We just need to compute, at every step of learning, we need to have this target. Now, like, let's say this was the Monte Carlo return target, like G sub t. Now, from earlier, when we had this Monte Carlo target, we could only use it when we reached the end of an episode. And for any lambda which is greater than 0, right? Because when lambda is 0, we only have this one step. That's what I was showing here. When lambda is 0, we only have to worry about the one-step return, and we don't have to wait for the end of the episode. But if lambda is any non-zero value, you can't like see them easily here, but we do have non-zero weights for all of these terms. If I zoom in here, you can see, they're shrinking pretty quickly, but there are non-zero weights that down here. And in order to actually know this return value, we have to have all of the data to the end of the episode, right? Like we have to have the entire string of returns to termination, which is why this is an offline algorithm, kind of like the Monte Carlo algorithm, where we have to run an episode, wait for it to complete, and then take all of the entire string of information and use that. Now, once we have the list of rewards, like here, like let's say we have access to this entire list of rewards, we could compute the lambda return in this way by its definition, where we look forward in time, one step, then we look forward 2 steps, 3, and we compute, a different, each one of the discounted sums. Now, if you were doing that forward in time, right, like you could build, I'm trying to think, yeah, like there's a way to compute this incrementally going forward as well, right? Because this is going to be R1 plus gamma R2, and this is going to be R1 plus gamma R2 plus gamma squared R3, and then this. So, but you have to end up, continually multiplying by gamma. But it's a little more straightforward if you go backwards and use this recursive formula. Sorry, not that one. The recursive formula you discover in this exercise solution. So yeah, this in the book, they mention this update rule. You'll notice like that there's no pseudocode for this algorithm because, well, if they put the pseudocode in, I guess they would have to reveal the answer to this exercise, right? Because we need a way of computing this for every value of t. So I will show this is, oh, sorry. So this is just the n-step algorithm from chapter 7. But this is the offline lambda return algorithm implemented. I only implemented it here for this random walk example, which is a Markov reward process. So this is sort of overly simplified. This is just more for demonstration purposes. You wouldn't really use this algorithm for anything because it has a lot of limitations compared to the TD lambda algorithm that we're going to get to. But here, the way this works is this function will run an episode and then it will generate this list. So it'll generate a list of the states and rewards. And then what this does is it goes through the list of states and rewards and it starts at the endpoint. So it initializes the lambda return here as the final reward value, right? So this R sub t value. And then whatever the estimation method we're using, with the parameters, right? Because we're assuming like here, right? We have this v hat that we're using for estimation. And these are the parameters that we're going to update. So we compute the v hat not at the terminal state, because that by definition has a value of 0, but at this s sub t minus 1. So we're going to initialize that there. And then this is the recursive update rule for the lambda return, right? So this is the reward value. So like we have this return initialized, right? This is initialized at the final reward value. And then this is going to be the reward one step prior to that. And this is going to be the v hat, or the function approximation at the state right before this. And then, right, this is this initial value of the lambda return, which is this r sub t. So once we initialize g lambda, then this just updates g lambda incrementally at every time step going backwards, which means that because once we've selected a value of lambda, not only do we don't even need to keep track of all these the individual n step returns, because this update rule just keeps track of the lambda return at that particular time step. So it's going to sort of compute this entire cascade of n step returns at every single time step in the episode, right? So like this is showing what the g lambda is at time step t, but right, in order to compute these weight updates, we need to not only have this at time step t, but this at every single time step along the episode, right? So this entire collection of sums has to be like we need to have something that computes the value of this at every step t. So that's what this does, and then yeah, it ends up doing this parameter update using everything else is filled in. This gradient term we already have talked about this earlier, but this you just get from whatever you're using for function approximation. And then yeah, and then you can just repeat this for multiple episodes. So, but again, this algorithm will only work for an episodic problem, right? Because first we have to run the episode, and then we have to, do this weight update and compute the lambda return at every step. So we had previously looked at this random walk example. I think it was introduced in chapter 6. So, wait, is this right? Random. Yeah, and they don't really repeat showing the example here, but the random walk example is just a problem where there's a starting state in the middle, and then there are states to the right and left of it. There's an even number to the right and left, depending on how large the random walk is. In this case, the one being shown here is actually for a 19 state random walk. So, this only goes up to 10, or I guess it should do an odd number, so it's in the middle. But yeah, so imagine this just larger. So yeah, there's just 9 states on either side of the central state. And then there's a terminal state to the right and to the left. In this case, the actual reward for exiting right is 1, just like it is here. And then for exiting left, instead of 0, it's -1. That just makes the value symmetric. The true values are just symmetric about 0. Here, the true values are centered at 0.5. But if you make this left reward -1, the line looks the same. It's just this is stretched down so that the central state has a value of 0, and then the far left state has a value approaching -1 and approaching +1 on the right side. Right, so this is a Markov reward process, so there's just a random chance of transitioning either right or left from every state. So here I'll show, this is just an example of how the trajectory would go. It's just bouncing around randomly, and then eventually, like the longer the random walk is, so 19 is quite long, then the longer you expect to spend bouncing around before you exit a particular side. And this is actually 71 steps until it exits. And there's an equal chance of exiting to the right or left because it's all random here. So in this case, it exited to the right, and then it produced a reward of +1. So that's, seeing it in animation. This is like showing the actual sequence of states of all 71 states, and then this is the reward sequence. So the reward sequence is 0 on every step, and then on the final step, it's 1. If it had exited to the left in the problem they're showing here, then this final reward value would be -1. So that's the problem we are considering. And the true values look something like this, but with this left value being close to -1, but there are these linear values. And the idea, like normally we do function approximation in problems where like you can't represent all the states, and that was sort of the subject of earlier chapters. In this chapter, because we're introducing this new update target, this is actually just a tabular problem. And there is going to be a list of parameters here, but there's only going to be 19 parameters, and each parameter is just going to represent one of the states, right? So this algorithm, just like all the function approximation techniques we had talked about, they all can be used in tabular problems. It's just a trivial subset of these approximations. But in the tabular case, the v hat, actually I have it written out here how, a little later down, how the tabular method works. Yeah, so we had, in general, this gradient could be anything. This could be any parameterized function, but often we look at linear approximation. So in the case of linear approximation, v hat, there's some weight vector, and there is some function which takes a state and puts it in a state representation vector. And that vector has to have the same length as the weight vector for linear approximation. And then the v hat function is just the inner product of the weight vector and the feature vector of that state, right? This is just written out as a dot product. This is what the dot product is. It's just this sum. And then the gradient has a very simple form. The gradient is just the feature vector here. So this is what, for linear approximation, what this gradient is, and then this v hat. And then in the case of a tabular problem, it's even simpler. In a tabular problem, right, just like in this random walk, there's 19 states. So there is some list of states. Let's say D is the number of states. And then there's a weight vector of size D. So there's one weight per state. And then v hat of state I is just Wi. And the gradient, all of the gradients are just these one-hot vectors. So the gradient of state S1 is just the vector of 1, and then the rest are zeros. The gradient of 2 is this. And then you can see that in this update rule, whatever state you're in, when you do the gradient update, the only W that's affected is the one that corresponds to that state, which is what makes this a tabular problem where all of the states are independent. So this algorithm ends up being like, if you did this with lambda is 0 or 1 in the tabular case, it would be exactly the same as the tabular solution methods from part 1 of the book, where we had either the TD0 method or the Monte Carlo method. But now we have access to these other values of lambda. But yeah, this tabular problem is just a trivial version of function approximation where the gradients have this very simple form. So because this problem is just, a tabular problem, actually, the way I implemented TD lambda later is just using the tabular problem directly and using these rules. You can also write this out as a form of state aggregation where you do have like a state representation, but it's just a trivial representation because they're also they're all these one-hot vectors. But you don't even have to bother forming these because if you want to look up the value of a state, you can just grab the parameter value for that state index. So, for this random walk, I showed earlier, like, we know what the true values are. You can just compute these analytically, what the true values are. And actually, in here, this is the formula for computing the true values. So it's just, and here we usually have an odd number of states for these problems. So it's just the number of states plus 1 divided by 2. So here it would be 10. And then the true values are just starting at, 1 minus 10 over 10. So like negative 0.9 up to 0.9. And then it's just a linear relationship. So what this is plotting here is at the end of an episode, we have the list of parameters, and there's one parameter for each state. And those parameter values are our estimate for the true values. So we know what the true values are, and this is just showing the root mean squared error between the true values and the estimated values only for the first 10 episodes of training. This is looking basically, how quickly is this method converging to the true values for this problem. And here from chapter 7, right, this was the tabular n-step method we had from chapter 7. And notice that, there's some intermediate value of n that seems to be converging the fastest. Here, yeah, this is showing the n-step method and the offline lambda return method. And it turns out actually computing this method is a lot faster than the n-step method is pretty cumbersome the way it's computed. But here, the intermediate value of n that converges the fastest is 4, and the value of lambda is 0.8. We could also go back to the half-life and see, let's see, a lambda of 0.8 has a half-life of 3, as opposed to the n-step value of 4. But again, like this is a half-life of 3, meaning, the 3-step return is going to be weighted half of the 1-step return. Or the 4, actually, no, this is, yeah, the initial return is 1, is the 1-step return, right? So this is saying, yeah, comparing, yeah, I believe the 4-step return to the 1-step return. So basically, once you get to the 4-step return, it's weighted half as much as the 1-step return. So there is some connection between these two. But, 0.8 is quite, like, that is, quite a bit along the way to the Monte Carlo return. And what we saw in chapter 7 is that if you make the chain shorter, then the bootstrapping matters less. So if I make this just like a 5-state random walk, now you can see that n equals 1 and lambda equals 0, which is it should be the equivalent algorithm, end up being the most efficient. And then it's only as we start, increasing the length of the chain that you end up favoring these, higher values of n. And that just means that, we're collecting more returns into the future, relying less on bootstrapping in the early phases of the problem. And it makes sense because as the chain is bigger, you have more bootstrap values that are early on going to be very far away from the true value. So it would make sense that in the early part of training, you would want to rely less on bootstrapping. Yeah, but this is just showing that, this offline lambda return is just another way of getting a similar result to what you get with the n-step methods that we had before. Yeah, so that's this example. Is there any question about this? The comparison between the lambda return and the n-step method?
Yeah, I don't really have any question concerning the difference between the offline lambda return algorithm and then the n-step TD method of how having a higher amount of states in a random walk basically gives a preference for having a larger amount of steps, essentially.
Mm-hmm. Now, this offline algorithm, like I said, in order to use this, we have to have this whole chain of returns to the future, which, is the forward view. Now, ironically, the way I actually implemented this, it is looking backwards instead of forward, or at least it's computing things going backwards. But the point of the forward view is that in order to get your answer at t, you do need all of the forward time steps to have been completed already. Just like with the n-step method, if it's like n equals 5, you need to have the results 5 steps in the future before you can use it. Now, TD lambda is going to be a very different approach, which is going to introduce the eligibility trace. And this is going to transform the algorithm into an online method so that at any moment in time, we can, we might not have the full chain of rewards, but let's say like we eventually reach the end. The point of TD lambda is that by the time we reach the end, all of the updates we would have done will end up computing the right thing. But along the way, we're not going to wait until the very end to compute it. We can actually incrementally start accumulating these results along the way. But initially, we're just given what the algorithm is. And the algorithm is going to introduce this new thing called the eligibility trace. And it's a vector which is the same shape as the weight vector. So in the case of linear approximation, it's just a vector of size, d. So it's just going to mimic the weight vector. And it will also mimic the feature vector, right, in linear approximation. We have those x's because they also match the same size as the weight vector. So there is a rule for incrementally updating the eligibility trace, which is before we start learning, we initialize it at all values of 0. And then we add to that the gradient of the approximation function at the state at time t, right? And this gradient, like I said, in linear approximation, it's just going to be the feature vector. Or in the case of tabular, it's just going to be this thing. And you can see the form of this is we add a discounted copy of the previous eligibility vector, which is discounted by both lambda and the discount rate gamma. So what the eligibility trace is doing is it is accumulating the gradients of the previously visited states. And the rate at which the past states decay or contribute less to the eligibility trace is dependent on both gamma and lambda. So again, like in the extreme case, if lambda is 0, then we never consider the old trace, and the eligibility trace at any moment in time is always just the gradient. And now if you look at the update rule here, if z is just the gradient, then we just have the same algorithm as TD0, which was the semi-gradient TD0 method. And then if lambda is 1, then it's going to end up being equivalent to the Monte Carlo return, although it's a little harder to see that the way this works. It's going to accumulate all of the gradients. But by the time we reach the end of the episode, it will have added up all of the gradients and multiplied by the TD error at each step. And it will also be equivalent to just computing the Monte Carlo return.
But it does make sense, given that since it's a recursive formula that having the lambda, if it's anything less than 1, then eventually stuff that's looked back will eventually be irrelevant. But if it's 1, then it would accumulate everything.
Mm-hmm. Yeah. So yeah, the closer lambda is to 1, the more it, the longer it takes for past states to decay away in their contribution. And that mimics how the lambda return, if lambda is close to 1, it considers the entire forward-looking history, right? But here, this TD lambda is this backward-looking view where, we started back here somewhere, and then by the time we get to this state, we can then add the updates to the past states that we didn't have the information for yet. And the idea is that, this state in the past somewhere, as we go further into the future, we're going to continue to accumulate updates to this state based on the rewards that we have yet to see into the future. But the algorithm is just given by this. This is the way to update the eligibility vector. Then we have the individual TD returns or TD errors, which are just the one-step TD errors we had from before. And they are the only things we need to compute on every time step other than the gradient. And then the weight update rule is just going to replace what was this gradient term with the eligibility vector, which is now an accumulation of gradients going back in time. So the algorithm looks, it should look very similar to the semi-gradient TD0 algorithm, which maybe I show it, was it in chapter 9? Let's see, semi-gradient TD0. Oh, well, I guess I don't have pseudocode for it here, but it should look almost the same with now this additional eligibility vector that we're accumulating. Normally to do TD0, to do TD0, just imagine that lambda is 0 here, and then z is just the gradient, and we just have this update rule where we're using the gradient. here instead of an accumulation of gradients. But once we define this algorithm, we also get the TD semi-gradient TD0 algorithm from chapter 9. It's just we also have this other family of algorithms. And here, let me just show how this is implemented. Okay, so this code, it looks a little more complicated than the pseudocode because I'm basically, a lot of these things I'm updating. So there's a function, like for example, there's a function to update the gradient based on not the state, but the state representation vector. So there's a function to update the state representation, which is used. And that's that function I showed defined earlier. Right, for linear approximation, this will be just a vector of dimension d, where d is the number of parameters. And because like once I update the representation, then I can use that to compute the value estimate and to update the gradient. There's a function here that updates the gradient using the state representation and the current parameter values. And then, yeah, I mean, the part that looks most similar is just, this is the part where the transition is computed, where we get the reward and the transition state. Here you can see that looks almost the same as the update steps in here. So here, this is the update to the eligibility vector. And this is computing the one-step TD error and then the parameter update. And these are all, just basically copies of the code here. All of the other code is just handling all these cases of how you update the state representation and then actually get this gradient, and handling these edge cases, like once you reach a terminal state, you don't actually want to compute, like you have to reset the episode here and then reset the eligibility vector to 0. But otherwise, I'm keeping copies of the value. I'm only updating the state representation once and then keeping track of what it is. Like, so here at the, like, I had already gotten what I needed out of the first state representation from the initial state before changing it, right? So from this point forward, this state representation is now the state S prime. And that's what ends up getting used here to compute the next value of v hat and the gradient value. So this, hopefully is like a pretty efficient way of doing this. And this algorithm handles either Markov reward processes or Markov decision processes. The difference is just, for one, you need a policy. So if you use an MDP here, you also need the policy function, but this ignores that because there's just this transition function, which in the case of having a policy, the transition is just defined as already using the policy function. So here, you're just passing the policy function into this step. So then this is just defining TD lambda for the general case of any kind of gradient. This is a version of it for linear approximation. So for linear approximation, the only thing you have to define other than, like the actual MDP and the value, all the parameter values, like gamma and lambda, is the number of parameters you're going to use for the approximation. So this is the size of the feature vector and the parameter vector. And then you also need to define how the state representation is updated. And once you've defined that, that's this x function here, then that's all you need for computing the gradient. Right, so the gradient update, it just sets the gradient to be the state representation vector. The value estimate is just the dot product. like I already said, and then it just runs this version of the function with the linear function approximation. And then there's also a version of this which is even simpler, which is for the tabular case. In the tabular case, you don't even need to update the state representation, really. All this does is keep track of what state you're in, which is just a single number. Like for the random walk, it's just, which of the 19 states you're in. And then the gradient update, it just sets the gradient at that state index to 1. So this is like the simplest form you could have, which is just, this is also a linear method, but you can make it even simpler than the general linear method with this tabular method. So then we can apply this algorithm to the same exact random walk problem, which is being shown here. So this is like before this earlier chart, we had compared it to the n-step method. This offline lambda return is like using the true value of the lambda return as the target. And we haven't shown here or proven that this eligibility trace approaches that. This is just showing empirically that the results of doing this are similar to the offline approach. You can see it certainly agrees with what like the value of lambda is that gives the best result. Like here they both agree on 0.8. And the actual like value it converges to also matches pretty closely. The main difference with the TD lambda return is if I start zooming out here, you can see that at higher learning rates, higher values of alpha, this method gets unstable and starts diverging. But in general, it does poorly if you choose a learning rate which is too high. Whereas the offline lambda return, you can see that at high learning rates, it's not doing very well over the first few episodes, but it's not diverging either. It's just, more stable in this regime. But if I reset this, if you go out to like more episodes, so here actually I'll just go to like 100 episodes because this chart is for the first 10 episodes. If you go out to like 100 here, what ends up happening is just this divergent behavior gets a little worse, whereas this ends up staying, like these are all staying stable, even though the results are worse. They're not like blowing up as the learning rate gets too large. So that's one caveat with this method is you do have to be careful about, as long as learning rate is small, then the results, certainly like the actual, like which lambda is the best value to use, those types of results will generally agree between the two methods. It's just the method isn't as stable. This formula is something that was mentioned earlier, which is, before when we had the TD0 method, we had shown what the TD fixed point was. And the TD fixed point are the parameters that minimize, or that the TD0 semi-gradient method converges to. And the goal is to find the parameters that minimize the value error. But the TD fixed point will not, in general, be the same point, the same set of parameters, but it is bounded to within, like it's guaranteed to be within this bound of the value error. And that was for TD0. Now, the Monte Carlo return is where lambda is 1. And you can see that there, the error bound is 0. So it's actually guaranteed to match the minimum value error. And then at these intermediate values of lambda and gamma, you just get some other bound. But generally, like the higher lambda is, then the closer the bound is to 0. Now, this is like just because this value is high, like here it's showing what the bound is for different values of gamma and lambda. As lambda approaches 1, the bound, shrinks. And it should approach, just approaching, well, it should approach 0. Okay, I'm not sure why it's not approaching 0, but yeah, you can see when lambda is 1, this approaches 0. But for TD 0, right, lambda is all the way on this other extreme end. So we would expect, we don't have much of a guarantee of the result being close to the minimum value error, but practically it doesn't differ too much, right? In chapter 9 for the random walk example, I might as well show it because we're also looking at the random walk here. This is showing what the values for the TD fixed point are versus the Monte Carlo values, and then the green line is the true values. So it's just showing, how far the TD fixed point. Yeah, these are the Monte Carlo values. I don't know if this is, yeah, I mean, you could get better convergence by changing the learning rate here too. But this is just an example of how the TD fixed point could differ from the Monte Carlo target. This is for TD 0. So whatever, and we had been using this and shown that empirically it does often converge to something close to the minimum value error. For this method, I mean, we can only do better because like whatever the value of gamma is, this value of lambda is something less than 1. So yeah, whereas like, typically this bound for TD 0 was with lambda is 0. So, the more we raise lambda, this bound only gets better. We already saw that empirically it was okay most of the time with the TD 0 method. So we just have a similar, concern here that we might not converge to the same parameters that we get from the Monte Carlo method. But, it's still going to be, in general, something better than we get for the TD 0 method. So yeah, that's a summary. Like this diagram is just showing empirically how this is approximating the offline lambda return. And then the next couple exercises are actually, proving that if you look at all the TD lambda updates and make some assumptions about when the weights are updated, then you end up getting the same result as the offline lambda return. So just sort of, justifying it. But that is actually doing these is, well, certainly for this exercise is a lot more detailed math. So we can wait until next time to do these exercises. And then the remainder of the chapter is just looking at some alternatives to TD lambda, which are a little bit more theoretically sound in some cases. In the case where we don't actually like reach a terminal state, it's just that along the way, like the problem with TD lambda is that we don't get the correct, collection of updates until we finish an episode. And these other methods, going to the end of the chapter and culminating with this true online TD lambda, are just computing something which should be the correct target value at every incremental point in the process. But they're just sort of extensions of the TD lambda algorithm. So you can try to explain those and maybe go over these exercises during the next session.